Hello, my name is John Pascoe, I'm from TU Delft, and today I want to discuss with you the topic of damage tolerance for fatigue after impact in fiber-reinforced polymer composites, particularly in the context of aerospace. Now, as you may well know, typically when we have an impact in a composite structure, what we get is a small dent in the visible impacted surface, but within the material we get much larger damage in the forms of delaminations. And this means that in order to find this impact damage, we need to do targeted inspections using specialized equipment. And that immediately raises the question, well, what happens between the time that we have the impact and the time that we actually inspect? And basically there are two possibilities. One is that nothing happens, the damage stays the size it is. And the second option is that over time the damage will grow. Now, the second option is currently not allowed by the airworthiness regulations. And this means that we have to design a structure so that the stresses and strain and release rate in the structure stay below the fatigue load or the fatigue threshold, even when there is a damage present. And that means we have a very large weight penalty because we need a lot of material to keep the stresses that low. From experience in metals, we know that we can gain a lot of weight benefits by using the slow growth concept. In that concept, we have a certain initial damage. We know it will grow over time, and that if we wait too long, it will reach some critical value. But because we know what the critical value is, where the final failure occurs, and we know how the damage will grow, we can define an inspection window, which is the time frame within which we can find this damage and take corrective action without endangering safety. So why don't we use this in composite materials? Because we could expect similar weight benefits there. Well, that is because there are currently three major areas in which there are significant knowledge gaps that need to be addressed. First of all, there's the question of damage characterization. How do we characterize the damage we find? Secondly, there's a question of predicting how this damage will grow. And thirdly, there's the issue of critical damage size that we need to understand. So in the remainder of this presentation, I will tackle these topics one at a time. So let's start with the topic of damage characterization. We know that impact damage composites will generate matrix cracking, delaminations, and potentially fiber fracture. But because of the limitations of the inspection techniques we have, typically we tend to focus on the delaminations. And one immediate area of concern there is that typically we inspect using ultrasound, so we emit ultrasonic waves onto our material, and they get reflected back by the damage, which means that any delaminations close to the surface will shadow the delaminations located below them. So we already have an inherent limitation of the damage picture we get. Furthermore, if we look at how this damage is characterized, as I said, we focus mainly on delaminations and we look at the projected area typically. So we then characterize it in terms of either this total area or in terms of the width of the delamination, or the maximum width of this delaminated area. What we need to remember here, however, is that this is a two-dimensional representation of what is in fact a three-dimensional reality. And then we need to ask ourselves, are all the delaminations here equally important that we are projecting together? Is it in fact the biggest delamination that is the most important? Or is neither of those the case, and does it matter, adjacent to which ply a delamination is in order to determine which is more important? So how do we move forward in this area? Well, what we really need is a better understanding of the damage mechanisms, and this is where we should be focusing our research. We need to understand what damage types do we need to be able to detect. Does it matter that we don't see matrix cracks on a C-scan? And what is the best measure to really quantitatively express what is the severity of any damage we find during a scan? Once we have that, we can move on to the second topic, which is the actual fatigue delamination growth. The state of the art there is really summarized by this graph, which is already from quite some years ago, but still represents the state of the art, where we see that there is some initial damage growth, then there's a plateau region, and then there's a sudden acceleration of the damage growth again. Which of course raises the questions, well, what is happening in that plateau region? Is nothing going on there? And why do we get a sudden acceleration? Now it's important to remember here that this damage zone width, which is plotted here, is determined on basis of a two-dimensional projection. And if we have an actual laminate where we have delaminations at each interface in our laminate, which is typical for an impact case, and now imagine we look at the projection, then the width we see here will be the width of this largest delamination, because that is the one that will be projected. So we might have actual delamination growth that looks like this, where we see large delamination growth at these lower lying areas, but the width of the projected zone will only increase by the small amount based on the second delamination. So that gives the illusion of a plateau where not much growth is occurring, when there actually is a lot of growth happening. We can also imagine that once all these delaminations get similar in size, then all of a sudden all these delaminations might suddenly start growing much faster, and that could be that sudden acceleration we see here. Now for the moment this is a hypothesis, but I hope that we as a community could investigate and get a better understanding of what is actually going on. To add to that, it's worth pointing out that our current delamination propagation research tends to make use of standardized specimens such as DCB, ENF, which focus on one-dimensional damage growth. There's only a single delamination, and the mode mix during the test is constant. Now contrast that with the real situation. We have two-dimensional delaminations, which also grow in 2 dimensions. It's a planar growth. There are multiple delaminations, which may all be influencing each other. And the mode mix is changing, both potentially during the load cycle, but also if we look around the contour of each delamination, we wouldn't expect the same mode mix at each location around the contour. So again, how do we move forward? Well, first of all, what we need is 2-dimensional growth test setups where we can really investigate and get a better understanding of planar delamination growth. And one recent example is the test setup proposed by Composites and her co-workers. We also need to wonder, is the strain energy release rate really the best way of characterizing the damage growth or the driving force? Or should we perhaps look at something like the strain energy density, which doesn't depend on the mode mixity? And there's some current research going on at TU Delft, which will hopefully be published soon, which looks into this question. Next, we can also think about how do we model this delamination growth, especially how do we model the 2-dimensional aspect and decide in which direction will the damage grow. And recent methods have been proposed to deal with that, which include the growth driving direction suggested by Carreras and co-workers, who suggest we should look at the gradient of isolines, damage isolines in cohesive zones. But we could also adapt the level set method, which has already been shown to work also for predicting 2-dimensional delamination growths. And finally, we need to look into understanding the interaction between different delaminations. Now, if we look at our current models, typically we also model delamination propagation, but this is computationally very expensive. Instead, we could do a parametric study like I did some years ago. This was for an adhesive bond, where we see that we have 2 delaminations, and on the other side of the specimen another 2, which have potentially different lengths. Now what you can see is if you fix these delaminations, so you do not allow them to actually grow, but you just measure the strain energy release rate in your numerical model. So it's a relatively cheap analysis because there's no propagation of damage that needs to be taken into account. You can still see that changing the relative lengths of these delaminations can cause huge differences in the local strain energy release rates at each crack tip. So this gives us a lot of insight into what is going on, how this damage will evolve further, without actually needing to go to the expense of actually propagating the damage within the numerical model. And we could use this technique to further understand what is happening in the case of an impact or impact damage. And finally, there's the issue of final failure. Now, in the case of final failure, the state of the art is typically as follows. We assume a certain known impact in terms of energy, impacted geometry, boundary conditions, etc. We simulate the damage caused by that impact. Then we apply a compressive load to this damage model, and we simulate the progression of damage due to that compressive load. And that finally then gives us the residual strength. And a recent example is, for example, the work of Sun and Hallett. Now, his work is very impressive. It gives good agreement of experiments, gives us insight into the damage processes which may be going on, but it's also computationally very expensive, and each run of the model is suitable only for one impact on one layup on one geometry, which is quite limited in size. Furthermore, let's look at what we need in practice. Well, in practice, we don't have a known impact. Typically, we find the damage, so the impact itself is unknown, and instead the damage is known because we have non-destructive inspection indications. Also, we're not interested in the total residual strength of the structure. What we're interested in is how long can the structure carry design limit load, right? And at what point will the damage have grown so far that it can no longer carry this? In other words, we don't need the residual strength for a given damage, but we need to know the critical damage size. And then we need to be able to predict how long will the structure take to get to that critical damage size. Also, you will find there's some debate in the literature of what actually causes this final failure. Sun and Hallett point to the importance of delaminations, and especially when these delamination growth may become unstable. Whereas Nettles and Sharber point much more to fiber failure and say delamination growth doesn't play much of a role. The structure fails when the fibers fail due to stress concentrations. And there's a mixture which has been suggested by Yang and Lee, who say, well, actually these are competing mechanisms, and depending on your initial delamination configuration, either unstable delamination or fiber failure will be the critical damage mode. So again, the way forward lies into a better understanding of the failure mechanisms, right? What is actually the critical damage mode? Are there competition between modes, and what determines then which becomes critical? And we need to be able to determine critical damage envelopes. So instead of going from a known damage to predicted residual strength, we need to go from a known limit load and be able to predict which damage envelope will be the critical one that causes failure at that load. So let's summarize this. Over this presentation, I've tried to convince you that if we can go to a slow growth treatment of fatigue after impact, that will bring us benefits. But in order to be able to do that, we need to change our research focus and address certain knowledge gaps. These are in particular, we need to better understand how to characterize damage, how to quantify its severity. We need to understand two-dimensional fatigue delamination growth, and we need to be able to define critical damage envelopes that will cause failure at a given load. Now, there's a lot of work to be done in these areas. I look forward to working in this area over a couple of the next years to address these topics. I hope you will join me in that, and I look forward to discussing these issues further with you during the discussion session. Thank you very much.